Hi, everybody. This is the last lecture of the geometric discrepancy theory mini course. Thank you, everybody, for coming. It's a pleasure teaching for you guys. Um, so today's lecture is it's again disjoint from the previous two lectures. So if you haven't listened much, you can just start listening from scratch. Um, we will talk about the application of Fourier methods in discrepancy theory. So, as I said, the whole course is somehow focused on the applications of analysis in discrepancy theory. So I'm primarily an analyst. My PhD was in harmonic analysis, and I consider myself a harmonic analyst. So, um, well, actually, we've already seen some applications of. You can argue this is Fourier analysis or definitely harmonic analysis when we talked about Haar function expansions of the discrepancy function. Or Haar functions are wavelets. Well, this is an orthogonal expansion. That all orthogonal expansions which that involve oscillations can be considered Fourier methods. But in this lecture, we will deal with the methods which are purely Fourier. So we will the lecture will consist of three parts, and the first part actually goes back to the very basics of the theory. And the whole theory started with a seminal paper of Hermann Weyl from 1916, if I'm not mistaken. It was called Uniform Distributions of Sequences, this in German. Okay, so let me give you the main object. Let's start with the main notion. So the notion that Hermann Weyl introduced in that paper is the notion of uniform distribution of the sequence, and it's the following. So assume you have a sequence in the unit interval, okay, and the sequence is called uniformly distributed if when you take any interval, any subinterval in 0, 1, and you compute the following quantity. You look at the number of points from your sequence. You take the first capital N points. Okay, so cut off your sequence at capital N, take the first capital N points and count how many of them lie in that interval. Okay. And you divide by N, which means you're taking the proportion of points that fall into the interval. Okay, and asymptotically, as N goes to infinity, you want this to converge to the length of the interval. So that means that every interval in the limit gets a fair share of the points. Okay, so this notion plays an important role in number theory. So at that moment, Hermann Weyl was interested in number theory. It comes up in ergodic theory. This property is some sort of ergodicity, and in many other areas. Okay. So let's try to just briefly heuristically analyze this property. Well, if you think about it for a little bit, you can see immediately that if you take the function f to be the indicator function of an interval, then this relation is exactly this, right? On the right-hand side, you have the length of the interval, which is the integral of the indicator function. And on the right-hand side, you would be counting how many times you fall into the interval. Well, now you can approximate, for example, continuous functions by step functions, and you use this property, and then you would see that this property also holds for all continuous functions. So it's a pretty easy argument. Okay, so this is actually so you have a certain ergodic property that time averages are equal to space averages for all continuous functions. Okay, and then you can also use the fact that any continuous function can be approximated by a trigonometric polynomial to prove the following criterion, which is known as the Weyl criterion. It was proved in Weyl's paper. So instead of considering all continuous functions, it's enough to consider complex exponentials. Okay. So complex exponentials, you can approximate all functions by trigonometric polynomials, as I said. So for a constant function, you obviously should get 1. Okay, and all these complex exponentials for all non-zero integer k, they give you, they should give you 0 because that's their integral. Okay. So the while criterion gives you an more analytic way to test that the sequence is uniformly distributed. So it might not be as easy to check it for all intervals, but often it's much easier to check it for all complex exponentials, so for all oscillations. But before I show you an application of this criterion, it has many applications, but there is one which is absolutely immediate and which is very, very simple. I want to try to explain it geometrically, and I want to explain the idea and logic behind it. So why this criterion actually makes sense. So for a moment, let's think that k is equal to 1. Okay. So let's think there is nothing here. So what you're doing here then is you're putting your points. So you had some points on the unit interval, and you're taking those points and you're putting them on the circle instead. So you take the unit circle, put your points there, and then you're adding them up and dividing by n. Well, you're just calculating the center of mass, right? So, and yeah, if the sequence is to be uniformly distributed, well, you want this center of mass to be 0. Okay, that makes sense. So this is a sufficient condition, but this is definitely not. Sorry, this is a necessary condition, but definitely not sufficient, because you could have a center of k equal to 1. You could have the center of mass at 0, but the points could be, for example, concentrated here. You could keep going like this, and the center of mass would be at 0, but this is definitely not a uniformly distributed sequence. Well, but this particular case is taken care of by the case k equal to 2. If you take k equal to 2, then all the points would collapse here, and then you wouldn't have center of mass at 0. Okay. And other values of k take care of the situation when you have points concentrated at the vertices of a regular k-gon. Okay, so in this case, you would still have center of mass at 0, but if you multiply by 5, they would all collapse into 1 point. So this property would not be satisfied. So this is the geometric explanation of the Weil criterion. So I hope the definitions are clear, the uniform distribution. Notice that the notion of uniform distribution of the sequence is pretty strong. Well, in particular, it obviously implies that the sequence has to be dense in the unit interval, right? But it implies much more, because you could have a sequence which is dense. Let's say you put 2 points here, 3 points here, then 1 point here, then 3 more points here, then 1 point here, then another 3 points here, then 1 point here, and so on. In the end, if you do it that way, this will be a dense set, but the sequence is not uniformly distributed. So here the order of the points also matters a lot, because when you talk about density, you're just talking about the property of a set. Here you're actually talking about the property of a sequence. You care about the ordering. All right. Okay, so as I said, let me give you one immediate application of the Weil criterion. Okay, so this is application to the so-called Kronecker sequence. It's a very famous sequence. I'm sure you've seen it somewhere. Well, we've already seen it in some examples. So this is sequence fractional part n alpha, where alpha is an irrational number. Okay, well, obviously, if alpha is a rational number, it's then for rational numbers, after a while, the sequence will just start repeating itself, right? At some point, n alpha will become an integer, so the fractional part is 0, and then it just repeats itself. And you just get a few equispaced points, but that's it. So that's not a very interesting case. But if you take an irrational number alpha, then you can easily compute these sums. Okay, so this just becomes, so the fractional part no longer matters, because these numbers are in the exponents, and then this just becomes a geometric progression. So you just compute the sum of the geometric progressions. This is what you get. And then, okay, this you can just bound by 2. Okay, this is modulus 1, modulus 1. Okay, and this is just some fixed number independent of n. Okay, so the whole thing is bounded by 1 over n, and as n goes to infinity, this goes to 0, so while criterion applies, and we see that this sequence is uniformly distributed. So you see that it is a very powerful criterion, because I could challenge you to think about this problem a little bit and try to prove it directly without using the while criterion. It's not impossible, but it would be much, much harder to prove it without the while criterion. Okay. Proving that this sequence is dense whenever alpha is irrational is very easy. It's a very common math Olympiad problem. It comes up in many. There are many applications of this. There are many math Olympiad problems which use that property. But proving that it's actually not just dense but actually uniformly distributed is much harder unless you use the while criterion. You see that the while criterion becomes essentially one line. Okay. So this already, you can see this is an application of harmonic analysis, because these complex exponentials and exponential sums, they come up pretty naturally. This is a very big topic which I just wanted to touch briefly. I wanted to show this to you just because it's the start of the whole theory. Okay, so let's move on. So I'll talk a little bit more about sequences. So now that you know that, okay, these things, let me go back to the definition. If you want to know that these quantities have to converge to I, well, you want to ask what's the rate of conversion, how fast that can happen. Okay. And that's where discrepancy comes in. So here you can also define discrepancy. Notice again, I do not normalize. So in some papers or books, you will see this normalized. You will see n here. So I will prefer, and actually this is how in many papers people write discrepancy, they do not normalize it. So this is essentially up to where you place this n, here or here. This is the rate of convergence, the definition of the uniform distribution. Okay, so you fix an interval, okay, and you look at the difference between the two quantities. You look at the rate of convergence. And van der Korput, I think back in 1930s or 20s, asked the question, is it possible for the supremum of this quantity, so you take the extremal discrepancy, you take the supremum over all possible intervals, okay, is it possible for the supremum to stay bounded as n goes to infinity? And he actually didn't just ask, he sort of conjectured that it is impossible. So I think the exact wording in his paper was something like, well, I do not know of any sequence for which this quantity stays bounded. Okay. And it took some time. I think in 1940s, Van Aert and Ehrenfest proved that it is actually impossible, that the discrepancy has to be unbounded. So this unnormalized discrepancy, in this formulation, it has to be unbounded. Okay, so the rate of convergence cannot be 1 over n. It has to be strictly greater than 1 over n. So it's 1 over n multiplied by something unbounded. So she gave a pretty weak quantitative bound. It was something like a double logarithm, like log n to some power. But still, she was the first one to prove van der Korput's conjecture that the discrepancy of any sequence is unbounded. So this was the birth of the theory of irregularities of distributions that I mentioned in the first lecture. We talked about a lot in the first lecture, which basically says that discrete object cannot approximate continuous objects too well. There is always some limitation. Um, so here is a very stupid example of the uh, of a result in irregularities of distribution. So you can also state that irregularities of the main principle of irregularities of distribution is that things cannot get too close to their average value. And here is a very simple argument, a very simple example, which we will actually use a little bit later in this lecture. Okay, so here you're rolling a die, right? And you're looking at the number that you get, and you're comparing it to the average, okay, to the expected value. So this is a discrepancy in some sense, right? So you have the expected value and you have the actual value. Well, and it's easy to see that it's at least 1/2, right? Because the expectation is 3.5 and x is an integer, right? So you cannot get closer to 1/2. They're closer than 1/2 to the average. Okay, as I said, it's very stupid, but we will see this later. But this, you can view this as some sort of a start of irregularity of distributions. Okay. And one of the last things I want to say about sequences is that Klaus Roth, whom we mentioned a lot in the first lecture, actually realized that this problem, understanding the bounds on the discrepancy of a sequence, can be restated. It's actually equivalent to the problem for fixed point sets in 2 dimensions. So here are the sequences in 1 dimension, okay, and now we have fixed point sets and point sets in dimension 2 on the unit square. Okay. The idea of this is the following. Basically, you can think about the index or time in the first case as the second dimension. So in one of the directions, it's not hard to prove this theorem. You take the graph of your sequence, okay, you stop somewhere, and then you squeeze it so that it lives in the unit square. So basically, that point set is the squeezed graph of your sequence. And then if you know bounds for the discrepancy of the point set, you would know bounds for the discrepancy of the sequence. Okay. Right. The other direction is a little bit more complicated, but still it's fairly elementary. So it turns out that these 2 problems are equivalents of this dynamic problem. So here you have a sequence, you keep adding points to the set. So you don't change the initial chunk of your sequence, you just keep adding points. And here you have all possible endpoint distributions. So just find an endpoint distribution, and you need to have the lower. So lower bounds in these cases are the same. Okay. And more generally, you can actually prove that if you put dimension d here, if you have d-dimensional sequences, that just there is an equivalence at the cost of 1 extra dimension. Notice that the formulation is slightly different. In the dynamic setting for the sequences, the lower bound holds not for every n, but for infinitely many values of n. And this is actually quite natural. If you think of sequences, so say we're in the unit interval, and you start putting a sequence, you can at some point achieve very small discrepancy. Like at some point, you could just have equidistributed points, equispaced points, and it's easy to see that they have very low discrepancy. But as you keep adding more points, at some point, it will have to be large again. Then maybe it will even out again, but then you keep adding more, and at some point it has to become large. So that's the reason that in this formulation, this is actually for infinitely many n. But one nice thing is that this formulation is actually the formulation that we've discussed in the first lecture. Okay, and this was the birth of the geometric discrepancy theory, because Ross realized, okay, we now need to study this geometric discrepancy with respect to rectangles. So this quantity, I think this was the first slide that I started lecture number 1 with. So Ross was actually initially interested in this problem, but then he realized that it's equivalent to this problem, and then from then on he was studying this geometric problem. And that was also the birth of geometric discrepancy in some sense, because then after that people started studying other families of sets, so not necessarily axis parallel rectangles. So you can also look at other sets, and this is a slide that you have also already seen. So these are some of the classical examples of families. So this lecture number 1 was about axis parallel rectangles. Okay, and the bounds in the 2 following lines are very similar to the bounds for spherical caps that we have discussed in lecture 2. Okay, and then you have an even larger bound if you consider all convex sets. You can see that the bounds in all of these cases are almost tight. So you have the same power of n. The upper bound differs by a power of logarithm. Let me actually explain briefly what happens, especially for those of you who heard the discussion yesterday, or if you looked at or did the homework. The lower bounds in all of these examples are done using L2. So you replace the extremum, the supremum, by some quadratic average, just as we did for the spherical caps. And then you prove an L2 bound using analysis. And actually, the goal of this lecture, I will show you both of these bounds, at least on the level of ideas. And actually, in the L2 sense, for the L2 discrepancy, those bounds are sharp. Okay, and the sharpness can be proved using jittered sampling that you saw in homework and in the discussion session yesterday. Okay, so in the L2 sense, they're sharp, but if you use jittered sampling if you use jitter sampling for the L infinitive or the supremum discrepancy, you get this extra square root of log. Let me very briefly remind you how jitter sampling works. So you take your domain square in this case, divided into equal parts, squares, for example, and then in each of these squares, you choose one random point. So it's better than IID random because you avoid clustering and big gaps. Okay, so you have something like this. Where does the square root of log come from? Without going into details, let me try to convince you that the square root of log here is natural. Actually, if you look at the supremum discrepancy, you need to use some large deviation inequalities, right? You're looking at the supremum of some large collection of random variables. You want to see what's the probability that it can be large. Well, you look at the large deviation inequalities. And the large deviation inequalities, there are many of them, Chernoff, Hoeffding, Bernstein, they're all roughly of the same nature. Most of them tell you that the probabilities of large deviation behave in a sub-Gaussian way. So they're bounded by some function which looks like a Gaussian, e to the negative t squared over something. Well, the square root of log, that's actually the inverse function of the Gaussian. The inverse of e to the x squared, the square root of log. Okay, so that's actually how the square root of log appears. Okay. All right. Well, again, I mentioned this before. You see 2 different types of behavior. You have very small logarithmic discrepancy in the case when there are no rotations, when directions are fixed, and if rotations are involved, or if you have curvature, then you get discrepancy equal to some power of n. You have a much larger discrepancy. And I mentioned, one of you asked a question on Wednesday, what's the reasoning behind it? I don't have a very good geometric reasoning for specifically this behavior, but we will see now that it actually has to do with the Fourier transform. And this is a very known topic in harmonic analysis, that curvature rotations, they add something to the decay of the Fourier transform. All right. Again, you've seen this before. These all these bounds are generalized to higher dimensions. We'll do them in dimension 2. So the bounds that I'm talking about today, they actually are almost, well, there is no difficulty in these cases in going from 2 dimensions to d dimensions. For axis parallel boxes, you see it with, as we discussed in this extremal case, it's quite difficult. So there is a big relative, at least relatively, there is a big gap, and we don't even know what the right conjecture is. But this problem is very delicate because your optimal discrepancy is logarithmic in n, so it's very small in a sense. So it's very hard to capture the order of magnitude, the true order of magnitude. Here, there is not much difference whether you're taking dimension 2 or higher dimensions. And also you see that lower and upper bounds are almost of the same order. So the relative difference is very small. It's square root of log. Actually, it's an open question still. It's been an open question probably for about 50 years now. Does one really need the square root of log? So is there a square root of log here? Or maybe we don't need the square root of log here. Nobody knows. Okay. But at least relatively this difference is very, very, very small relative to the main order of magnitude. Okay, so I will now talk about this bound, the bound for rotated rectangles, and for simplicity, we'll actually do rotated squares. Okay, and you will see applications of Fourier analysis. Okay, so let's start with slightly more general setting. So we have a set of endpoints in the unit square. We consider some collection of sets, and I will, let's assume that these sets are symmetric. Well, we'll assume that the family is translation invariant. So for example, the family of squares, it's just a translation invariant. You take a square, translate it, it's still a square. And we shall, we'll start with a set that is symmetric. So let's start with something that lives at the origin. That's symmetric around the origin or symmetric around any point. This assumption is not super important. Okay, we'll view discrepancy as the measure. So discrepancy as discrepancy with respect to a given set A, you can view it as a measure. So you have a bunch of delta functions, okay, Dirac delta masses, okay, and you subtract n times the volume of A. Well, you intersect with 0, 1, okay, but we'll not care about it too much. So, and you want to look at the supremum of this quantity, okay, over all sets in your class. All right, so let's look at what happens when you consider translations. So you start with your set A, okay, you translate it by some value x, and you compute this measure. Well, you can write this measure as the integral of the indicator of A plus x, okay, and then this the integral with respect to the discrepancy measure. It's a signed measure of total mass 0, of course. Okay, but it's a measure we can integrate with respect to it. Okay, and then if you change, if you try to stick x here, well, you get the indicator of, well, technically minus a. If I want to put x minus y, so you would put y minus x, then you would get a. If you put x minus y, it's minus a. But if I assume there is some symmetry, this is a very minor thing. Okay. So now you look at this expression, well, and this is a convolution, right? It's a convolution of the indicator function of a minus a with the discrepancy measure. Okay. So it's very easy to write it as a convolution, and actually probably every time you see a convolution, your first instinct should be, oh, we probably should use Fourier transform, because Fourier transform diagonalizes convolution. Okay. All right, so recall the definition of the Fourier transform. Recall that we just showed that discrepancy can be written as a convolution, and then Fourier transform turns convolutions into products. Okay, so we can then write the Fourier transform discrepancy as a product of two parts. And notice one very nice thing that happens here is that now you've completely separated the geometry of your sets. So the set A, the test sets, they come up only here. Okay, and then your point set. So because remember, D is the just the measure. It's the Dirac deltas that depend on your point set minus n times the Lebesgue measure. Okay. So this part is the point component, and this part is the geometrical component. Okay. And then, as I said, the lower bounds will be L2 lower bound. So let's compute the L2 norm of this function. Okay. So again, you use this property and you use Plancherel. So it's the integral of these two components, the point component and the geometric component. Okay. I hope that is all clear so far. Notice that so far we haven't rotated anything. We just took, we started, say, with the cube, and we just look at the translations. So this function is just the discrepancy of translations of a fixed set. Okay, well, let's see. Can we prove something just for the translations? Okay, so here is the start of the argument, okay, or what we would want to be the argument. Okay, so if you look, let A be the a square, okay, a square of side lengths R. Okay. So here, first of all, I'm going to use the stupid bounds, okay. So if R is small, okay, say of this order, then the volume, say it's exactly that, for example, the volume of this square is going to be 1 over 4n. Okay, then you're multiplying by n, so you're getting 1/4, right? So here, so square it and multiply by n, you get 1/4, and then you subtract this from the number of points in the discrepancy, right? That's exactly the stupid example from a few slides ago. This is an integer. This is 1/4. So this is always bounded below by 1/4. You need to be a little bit careful about boundary effects, but generally, let's not worry about it. So the discrepancy for such squares is also going to be at least 1/4. So on the average, this discrepancy will be bounded below by some constant. Okay, again, remember this means that there's some constant. Okay, so all right. Well, now assume we could prove the following. Assume that if we increase R, okay, so let's let this be R naught. Okay, assume that if we increase R, increase the size of the square, assume that this geometric component grows at least linearly in R. Okay, assume you can see this increase. Okay, well, then you could go from this side lengths, you would increase it to roughly constant, roughly 1, well, say 1/4 or something like this. Okay, and then from this identity, so nothing would happen here, but this would increase, so the whole thing would increase exactly at the rate that you want, and you would get, if you check it, you would get exactly the value that you want. So if you had this linear increase in the side lengths, then you would get your bound. Okay. Unfortunately, this is too optimistic to expect that. That doesn't hold. Okay, so this Fourier transform is very easy to compute, right? You just need, it's a product function. It's a product of two one-dimensional functions. So you just compute two identical one-dimensional Fourier transforms. So this is what you get. This is the Fourier transform of the indicator function of the interval from -r/2 to r/2. Okay. So So one of the first computations that you do that you study Fourier analysis. Very, very easy to compute. Let's try to analyze this function a little bit. So look at some pictures. So here's the function. Here it is in the top line. Okay, so remember what we want. We want to see the dependence on R. We wanted to grow with R. And unfortunately, you really don't see this much because let's analyze. Well, you can only see the dependence on R when this is close to zero, right? Then you will see how things differ with R. Otherwise, well, this kills pretty much everything because, well, this is just bounded by one and this becomes large. And as you can see in the picture, as you move away from the origin, well, away from T1 equal to zero, then it's not, you cannot really see the dependence on R. Things essentially die out. So this tells you that you can see the dependence on R. At most, at best, you can see it near the axis, like this. Okay. But even then, that is not enough because near the axis, sometimes sign becomes zero and that zeroes things out, and there you also would not see dependence in R. Okay, so you have these zeros. Okay. All right. So let me actually show you a little bit more pictures which confirm this intuition. Okay, so I changed the value of R here. Okay, and you see that this what's happening is exactly what I said. So you see something on the around the axis. Okay, it's very small away from the axis. Okay, and also you have zeros every once in a while on the axis. Okay, so zeros are also your enemies. You want to prove the lower bound, so you want to somehow avoid zeros. Okay, so here are some more pictures. So depending on the scale here, you almost don't see, well, you see the zeros here, and you see that all of the dependence is really near the axis. Okay, so here you see everything, dependence near the axis, almost zero here, but still you have zeros near the axis. But this actually suggests a solution. So this tells you, okay, we probably cannot prove the bound for the squares as we wanted to, and we actually know that it's not true. And if you don't rotate the squares, you should be getting logarithmic discrepancy, but it suggests a remedy. So since we have this property, all of our dependencies on the axis, and also you have zeros, which are your enemies also on the axis, you can do two things. First, you average over dilations. Okay, so you change R a little bit, you tweak it, and that smears out these zeros. So at least on the axis, after this, you would not have problems. And now you want to bring this dependence on R from the axis to the whole plane. Okay, and to do that, you just average over all rotations. Okay, so you consider all possible rotations, that would correspond to rotations of the squares, and that brings the dependence from the axis to the whole plane, and that's exactly what we want. Okay, this is just the intuition. This is just the logic of the argument. You still have to actually do computations to prove it, but turns out that it works. Okay, so here you average over dilations. Okay, so here rho is the side length and theta is the rotation of the square. Okay, so you average over rotations in some region between R and 2R, so roughly comparable dilation, comparable side lengths that differ by at most a factor of 2. Okay, and you then average over all rotations. Okay. It's a little technical, this argument, but it's fairly elementary. It's a good exercise. So you get exactly the bound that you want, and then that means that for this quantity, for the rotated squares, we can actually use the argument that we've discussed a few slides ago. So we can start with this trivial bound for squares that have size, say 1/4n, where you trivially have discrepancy bounded below by some constant, and then you can blow it up in order to get discrepancy bounded below by some by n to the 1/4. Okay, so let me go back. So here, sorry, this was the argument that we wanted. So it didn't work for just a regular axis parallel square with side lengths r, but it is going to work for rotations. So this argument works. All right. Okay, and in the last 15 minutes, I will talk about another bound, which is very, very similar. So this is the bound for discrepancy with respect to circles. Okay. Somehow philosophically, it's almost the same. Well, and it's not surprising that you get the same quantity, the same power of n. It's also not surprising that similar Fourier methods should work because, well, you're averaged over rotations of the square. When you rotate the square and average, well, if you just average the indicator function, you would get something that contains a disk, but then there would be some smoother cutoff. Okay, so you wouldn't get exactly the indicator function of the disk. So the proof that I just presented to you was due to Joseph Beck, and the proof that I'm about to present for disks will be due to Montgomery, so it will use Fourier series instead of the Fourier transform, but in spirit it's very similar. Again, as I mentioned in some other cases, I don't know of any theorem that says that once you get a bound for one case, you actually get a bound for the other case. But they're super similar in the way they look in their philosophy, and also they're very similar to the bound that we proved last time for spherical caps. Okay, so let's go to the case of circles. So in this case, the setup will be a little bit different. So since I said we're going to use Fourier series, we're going to treat the unit square as the two-dimensional torus. We'll be looking at periodic discrepancy. All right, and again, we fix a circle of radius r, and we'll look at the discrepancy as a measure. Okay, so you write the discrepancy measure. Again, it's the sum of Dirac delta functions minus the Lebesgue. Oops, there should be an n here. I forgot it. N times the times volume. Okay, and then you can, in the very same way, you can write the discrepancy as the convolution of the indicator function of the disk and the discrepancy measure. So again, you take all possible shifts of a single disk, so fix the radius, and now consider all possible shifts of the disk. Okay, and again, the very same way, convolution becomes product when you consider the Fourier coefficients, and if you want to compute the L2 norm, it's just the you just use Plancherel to compute it, so you get a product. And again, you have a separation of the geometric part, geometric component, and the point component. Okay, so now you deal with the disks, and again, this is a very common thing that you often do in harmonic analysis classes. You can actually explicitly compute these coefficients. This is essentially the Fourier transform of a disk. Okay. I'm not going to do it. It's a little technical and you need special functions, but basically you get the Bessel function here. Okay, you get the Bessel function of the first kind, J1. Okay. What we will need now is the asymptotics of the Bessel function. That the asymptotics is well known. So it behaves as 1 over square root of x right, times this phase, this oscillation cosine of x with some phase shift. Okay, so this is the main term in the asymptotics. So this is what happens when x goes to infinity. But actually, it turns out that this asymptotic is actually it's a very, very good approximation. Okay. So you see that the indicator, the Fourier transform of the indicator of a disk decays as t to the power 3/2. Here you have power t to the negative 3/2, power -1, and another -1/2 from the Bessel function. So that's a standard if you compute Fourier transform of the of any convex body with non-vanishing Gaussian curvature, you're going to get decay of the order -3/2. If you compute, going back to our previous example, if the boundary is flat, if it doesn't have curvature, we did this for the square, you get the decay of the order -1 in some directions, in the flat directions. All right, so now let's try to use it. So, okay, we'll work with the point component and the geometric component separate, and we'll start with the geometric component. So let's try to understand what happens to these functions. So if I plot them, because of this cosine, you see that again we have lots of zeros, okay? And we're proving a lower bound, so zeros are enemies. You don't want to have zeros because they prevent you from proving the lower bound. Okay, how can we avoid it? We already know from the previous example that you can try to maybe average in dilations to smear out these zeros. Okay, so Montgomery actually noticed an interesting thing that you. Okay, let's renormalize it. So we take the square of this and we multiply by x. Okay. So it looks like this. Montgomery noticed an interesting thing. If you take J1 of x and J1 of 2x, so this is a dilation, but you use not the whole interval of dilations like we used in the previous argument, but you only use 2 points of dilation. Okay, so you just use the original function and also the same function dilated by 2. Okay. That they are somehow asynchronized, and now if you add those two, this will stay away from 0. Okay. So essentially, you are still using averaging over dilation, but this averaging now consists of just 2 points, and it turns out that this is enough in this case. So you average over dilations. Actually, for cosines, just for cosines, this would be quite easy to prove. For Bessel functions, you need some more work because the cosines, the cosines are just the initial term, right, in the asymptotic expansion. But for cosines, you could prove it in a few lines. Okay. But this is bounded from below. So that means that if you, so this is bounded from below by a constant. Okay, that means if you divide by x, you have a lower bound, 1 over x. Okay. Okay. So if you go back to the Fourier transform of the disk, that means that if you take the disk, well, 1 is not a good example here, say 1/4 and 1/2. So you take 2 different radii that differ by a factor of 2. Then the sum of the Fourier transforms is bounded below by 1 over t cubed. Notice that we have a square here, so if you take square roots, this will be t to the 3/2. That's exactly this order that we were just talking about. So you don't only have the upper bound, okay, but you also have the lower bound. But for the lower bound, you need this average, and you average over at least 2 radii. Okay. Okay. Now let's deal with the point component. So we want some lower bound on the point component. Okay. So the point components, if you look at the Fourier coefficients, it becomes very easy. So the Fourier coefficient, the zero's Fourier coefficient is just the integral of this measure, and that's 0. Because, and again, my bad, this multiplied by n, because this gives you total mass n, minus this also gives you total mass n. Okay, and all the other coefficients, well, the Lebesgue measure will not give you anything because all of the complex exponentials integrate to 0, and you will get these exponential sums from the point component. Okay, so this is for all non-zero values of t. Okay. All right. And then it's a pretty simple computation. I will not do it, but yeah, when I say, I'll send an updated version of the slides when it's included. I don't have much time to do it, but you can just square things out and carefully look at them, and you can bound this from below by the sum of the Fourier kernels. Okay. Okay, so here's what we do. Sorry, but I will just sum over t that live in some square. Okay, so from negative m to m, m. So I take all the integer points that live here in a big square. Okay, and I want to get some lower bound, and I can bound it by the Fourier kernel. But notice that here I'm summing up everything. Okay, including this same term when t is equal to 0. I will have to subtract it later on. Okay, so I can bound it by the Fourier kernels, and the nice thing about the Fourier kernels are positive. Okay, so I can drop all the non-diagonal terms. Okay, so I will only stay with the terms where I have 0 here, and I have n of those terms. So when the point p equals point q, okay. So I will get n of those terms, and each equals fm squared of 0. So that is m squared. The Fourier kernel is, so this is of the order m, m squared. Okay, 1 over m here. So you get it's m at 0. Okay, m by now is some parameter which we'll play around with in a moment. Okay. All right, so I get this lower bound for the sum of these exponential sums. Notice this is a bound that's independent of the set because we only used the diagonal terms where you get 0, 0 here. So you forget all the information of the set, about the set Pn. Okay, so you get this lower bound, m squared n here. Okay, but now instead of this quantity, I actually want a bound for this quantity, right? And the only difference is that here I need to subtract the case t1, t2 equals 0, 0, okay? When the vector t is 0, because in that case, the Fourier coefficient is 0, so I don't want to count it here. But in that case, you get, well, all of these terms will be equal to 1. You get n terms, and you square it. So you get n squared. So this is what you need to subtract. Okay. All right. So now I'm trying to put everything together. And this is actually my last slide. Okay, so I have this lower bound for the geometric component. Right? Okay. I have this lower bound for the point component. Okay. So this is for some square from negative m to m. So I'm looking at the big square. So instead of taking the sum over all of z2, I'm taking the sum over frequencies in this square, which I need to remove the 0. Okay, and I take the sum over all such frequencies. So this will be a lower bound to the sum over all of z2. Okay, and then I will just estimate the geometric component by 1 over m cubed from here. Okay, and I will estimate, and then I have the bound for this sum. So I get this expression. Okay, and well, now you need to optimize in m. Remember, I told you in the previous slide, m is a arbitrary parameter for now. This works for any m. Well, to optimize in m, so the terms that you have will be, what is it? It's n over m minus n squared over m cubed, right? You want these terms to be roughly of the same order, so you need to choose m to be of the order square root of n. we need to play around with the constant, and then this will be of the order square root of n, and this will be of the order square root of n. If you choose the constant carefully, then the difference will be of the order square root of n. Okay. So if you take square roots here, you'll get n to the power 1/4. That's exactly what we wanted to prove. Okay. So let me reiterate a little bit of what we have just proved. So we proved that there exists a disk of radius, say, of radius either 1/2 or say 1/4. So, or two radii of radius r0 or 2 r0. It actually works for any radius. You can, so there, choose a radius, and you can find a disk of radius either that's r0 or twice r0, which has large discrepancy. Unfortunately, and again, this is a very interesting open question, it is not known whether you can do it for just single radius. Or maybe it's also possible that for some radii it's not true, and for some radii it is true. Okay, and so we have proved two different lower bounds here, both using Fourier analysis, using Fourier transform and Fourier series. And I will stop here. I'm really grateful. This is the end of the course. Really grateful for you guys coming to the course. I'm grateful to everybody, but I'm especially grateful to the Ukrainian students who are in Ukraine. I admire you guys. I know it's a very difficult time, and I admire that you still find time and energy to do mathematics, to study mathematics. I wish you the best of luck. I wish victory to all of us, and Slava Ukraini. Thank you.
Героям слава. Thank you.